Lecture 2 of Math 347. The main thing we'll be talking about today are propositions. So let's start with the definition of that. A proposition is a sentence that is objectively true or false. It's important to note that a proposition is a statement that has to be either true or false. It cannot be both. It cannot be neither. One thing to note here is that it's okay if we don't know whether or not it's true or false. Here's some examples of propositions. 3 plus 4 equals 7 is a proposition. 99 minus 1 equals 403 is a proposition. There are extraterrestrial aliens on Earth right now is a proposition. Again, let's stress that a proposition doesn't have to be true. Well, the first proposition we've written down here is true, the second one is false, and the third one is unknown. At least it's unknown to me. Maybe there's something you know that I don't. Here's some examples of non-propositions. So for example, the statement compute 4 plus 3 is not a proposition. It's something you'd absolutely often see in a math course, but it's not a proposition in and of itself. It doesn't have a truth value or not. Now, one way to modify this, though, is we could say you have successfully computed 4 plus 3, and that is a proposition. Another one is the best number is e to the 2e. Your definition of best and my definition of best may be very different. Now let's talk about how to combine propositions. So it turns out that there are a lot of operations on propositions that we can combine to make more complicated propositions. These are sometimes known as and or, and not, and exclusive or, and there's more, but let's just do a few for now. So let's talk about and. And is a proposition that's only true if both of its parts are true. So P and Q is only true if P is Q and Q is true. That's where the and comes from. Or of two propositions is a proposition that is true if either of the propositions are true. So P could be true, Q could be true, and they could both be true. Now I want to stress, in English there's a bit of ambiguity. We use the word or in two ways. Sometimes in English we use the word or exclusively. Like we might say you can have this or that, but you can't have both. That's an exclusive or. Sometimes we use the word inclusively, and if we want to stress in English that we're using it inclusively, we'll put like an and/or. But in logic and in mathematics, or is always chosen to be inclusive. If we want to have the meaning of an exclusive or, there's a name for that operation. It's sometimes abbreviated XOR, for exclusive or. And that's going to be true if exactly one of the components is true, but not both. And then finally, we have an operation called not, which just reverses the truth value of any proposition. So if P is true, not P is false. If P is false, not P is true. One way to be more precise about this is to enumerate every possibility in an object that's called a truth table. Recall, if P and Q are propositions, each of them have to be true or false. And so the combination of P and Q means there's really only 4 possibilities. So we can always write down a 4-row truth table that tells us all the possibilities. So for example, if you look here, we have P and Q, and note that we have exactly one true value on the right-hand side. We have P or Q, which is true for 3 out of 4 of the choices, but not the 4th. We also have not P, simple enough, it just reverses P. And then we have the exclusive or, P XOR Q, which is sometimes written in this circle plus notation, which again is going to be true only if exactly one of these two propositions is true. Definition here. So there's 2 special types of propositions that come up all the time in mathematics, and we give them special names. They're called tautologies and contradictions. So a tautology is a proposition that is always true. A contradiction is a proposition that is always false. Here's some examples. First, note that P or not P is always a tautology. One way to see this is to note that when we have P and not P, exactly one of those is going to be true. And remember, when we take the or of 2 things, we only need one of them to be true. So no matter what the value of P is, P or not P will be true. Similarly, Q and not Q is a contradiction. Again, exactly one of Q and not Q will be true, therefore they can't both be true, therefore this and can't be true. Finally, this more complicated expression is also a tautology, and you can see one of the short videos that goes through the details for that. Another way that we can combine propositions is by using the conditional or implication. If we want to understand what P implies Q means, we want to think of it in shorthand as if P, then Q. We write out the truth table here, and we define this operation to have the following truth values. Is it's false only in one particular of the 4 cases, and that if P is true and Q is false. Anything else is considered true in terms of this implication. I'll say a bit about this in a minute, but it might seem weird that we choose that false implies true is true, but there are reasons for that. But let me also say that there are a lot of ways we actually say this in English. So all of the following are appropriate. We can say if P then Q, Q if P is sufficient for Q is necessary for P. These are all legitimate ways to say the same thing. To think of an example, let's say P is the proposition that Ben is from Chicago and Q is the proposition is that Ben is from Illinois. Then there are really 5 ways we can say this. We can say if Ben is from Chicago, then Ben is from Illinois. Ben is from Illinois if Ben is from Chicago, etc., etc. English has a lot of different ways of allowing us to say the same thing. What's nice about the math and the logic is that all of these disparate ways to say the same thing we write as one particular mathematical symbol, and that's P implies Q. So that leaves a lot of this ambiguity out. Now I'll just make a comment now. The fact that we choose false implies true to be true, I'll concede is weird. If you look in the text, and other places, you'll see that there's some really weird sounding sentences in English if you use this rule. However, I promise you, by the end of this course, it'll be very clear to you exactly why. Okay, last operator of today is what's called the biconditional, or the if and only if. So we define this operation by a truth table. P if and only if Q is defined to be true when P and Q agree. If P and Q are both true or both false, we count that as true. If P and Q have different values, we count that as false. If and only if in mathematics is sometimes abbreviated by the kind of weird word IFF, for if and only if. Now there's some algebraic facts that are really useful, and we'll talk about these in depth in the next lecture. So it's equivalent, instead of saying P implies Q, we can replace that with not P or Q. P if and only if Q is equivalent to saying P implies Q and Q implies P. As I said, these ideas are going to be very central in our ways we attack how to prove things. It's also true that P if and only if Q is the negation of P XOR Q, right? And in fact, I'll just say this. So if and only if and XOR are completely opposite of each other. One last thing. For any implication, there are 4 statements that are related to it. Okay, so whenever I say an implication, if I ever have P implies Q, there are 4 statements that we can write down that are related. So we say, so given P implies Q, we say the positive version of that statement is just itself, P implies Q. The converse of that statement is Q implies P. We flip the role of P and Q. The inverse of that statement is we negate P and negate Q and say not P implies not Q. And then finally the contrapositive, we kind of do both. We flip the roles of P and Q and we negate them. Now here's something that's extremely important in this class, is it turns out that the positive and the contrapositive are exactly the same, completely equivalent, okay? And one of our major proof techniques going forward is when we can't prove the positive statement, we replace it with its contrapositive and prove that. We'll talk about that a lot in the next lecture. Another sort of rookie mistake that students always make at this stage is to replace the positive with the converse, and that is not okay. The positive and the converse are not the same. We'll see many examples of how that breaks down.